Hello, my name is Raviv, and the purpose of this video is to visually explain the meaning of stability in control systems. This is clearly a very stable structure. Now it's about time to play. Let's play the Jenga. Clearly it went from stable system to marginally stable to unstable system. You may have been recently or sometime in a concert, just like this one. Notice that the speakers are pointing at the audience. Now the question is, what will happen if the speakers are going to be turned the other way around? Let's look at the following animation.
See how it goes with you. I know I want to be here. Let's take a look at me.
The signal from the microphone goes all the way to the speaker, then being picked up again by the microphone, then again to the speaker, again to the microphone, and so on and so forth, until before you know it, in a very short period of time, you hear this very annoying screech. We all know what's going to happen. The audience is going, in no time, is going to throw tomatoes at the performer. We don't really want to see these kind of things. It's not fun. What we saw here is that bounded input results in unbounded output, which is a sign of instability. Actually, you can try it at home. Let's look at what we have done in this video, in the next video. You can really try it at home. Try it. Okay, so now let's look at the following scenario. You go to a hotel and you try to take a shower. As you know, there are two knobs. One is blue knob and the other one is the red knob. The blue knob connects to the cold water and the red knob is connected to the hot water. So if it's too hot, what happens? If it's too hot for you, you actually adjust the hot knob, and if it's too cold for you, you adjust the cold knob. Everything is stable. You took a shower, everything is okay. When you wanted to have the water colder, you just made it colder. When you wanted to make it hotter, you made it hotter. Everything was perfect. Beautifully stable system. Now, on the same day in the afternoon, there was some repairs in your room. And unfortunately, the person who fixed the shower, took the red knob and put it next instead of the blue knob, and the blue knob instead of the red knob. Meaning that now the blue knob controls the hot water and the red knob controls the cold water. So you take a shower, what happens? If it's too hot, you try to make it colder, but because of this switch, you try to make it colder, but in fact you make it hotter, and vice versa. Before you know it, hot becomes hotter and cold becomes colder. And you know how long it takes for you to run away from the shower if it's too cold or too hot. This is a sign of unstable system. Let's build a paper airplane. What happens when we put the paper clips in front of the airplane? We can see there is more mass in front of the airplane right now. Now let's try to fly it. Let's make an experiment. Let's take it and just fly it. As you can see, the paper airplane flies beautifully forward. It doesn't move to the right, nor to the left, just forward. This is a stable system. On the other hand, let's try to do a different experiment. Let's now try to put the paper clips in the back. And we now try to fly the airplane again. As you can tell, when we fly it, the paper airplane cannot really fly forward very nicely, and it's basically unstable. So we saw two different airplanes, one stable that has the paper clips in the front, and the other one unstable that has the paper clips in the back. One is stable, the other one is unstable. Let's try to explain what is going on with this airplane. After all, what we had is same airplane. At one point we put the paper clips in the front, and the other point we put the paper clips in the back, and the airplane behaves completely differently. Let's try to get an unofficial explanation, which is called, let's call it aerodynamics explanation. There is something which is called center of pressure. This is a center that actually is equivalent to what lifts the plane up. It's about the center, somewhere near the center of the airplane. There is another thing which is called center of mass. Center of mass is where, if you take all the mass of the airplane together, where would be the center of that mass? Now, when the paper clips are in front, the center of mass is in front. When the paper clips are in the back, the center of mass is in the back. So what we have, center of pressure and center of mass. When the center of mass is in front of the center of pressure, the airplane flies beautifully forward. It's a very stable system and it flies forward. Stable system. However, when we have the paper clips in the back, the center of mass becomes behind the center of pressure and the system becomes unstable, and as you saw, the paper is tumbling. So the whole idea is about the relationship between center of pressure and center of mass. For stable system, you want to have center of mass in front of center of pressure. Unstable system, the center of mass is behind the center of pressure. Now we can start to quantify the whole idea of stability and instability. As you can see from the following, what's called S domain, there are two parts. The left-hand side of the S domain, which is green, and the right-hand side of the S domain, which is red. Now, in stability, we talk about BIBO stability. What is BIBO stability? BIBO stands for bounded input, bounded output. It means that if for literally any bounded input, you always get bounded output, then we call it BIBO stable system. BIBO stable system, if you try to sort of translate it to the S domain, it means that all poles, no exception, all the poles of the system must be in the left-hand side of the S-plane, must be in the green part of the S-plane. Even if one is not there, even if one pole is not there, then the system becomes unstable. Let's now try to relate it to the airplane, qualitatively. Again, only qualitatively. When the mass of the airplane was in front, the center of mass was in front of the center of pressure, the system was stable. We can say that all the poles of this particular system were in the left-hand side of the S-plane, in the green part. On the other hand, with the second airplane, where the center of mass was behind the center of pressure, the system was unstable because it has at least one pole in the right-hand side of the S-plane, in the red part of the S-plane. This is the idea behind BI/BO stability and how to relate it to our experiments we have just done. So we saw two extreme cases of the airplane. We can gradually move the pole from the left-hand side of the S-plane all the way to the right-hand side of the S-plane and actually overlay it with the S domain. Let's do it. We are going to see several different paper airplanes. Each one has the paper clip at different location. So it relates to the location of the airplane with respect to stability or instability. To reiterate, for BI/BO stability, all poles of the systems must be in the left-hand side of the S-plane. If one pole of the system is the right-hand side of the S-plane, it is unstable. As simple as that. Now, let's look at the airplanes again. Now we see one in the left-hand side, we see the other one in the right-hand side of the S-plane, and we also see something which is on the borderline in between. This is a borderline between stability and instability. This happens where the center of pressure is exactly at the same location at the center of mass. The following two examples are real examples of real airplanes. The first one is a Boeing 747. 747 is always stable in open loop, always stable. All its poles are in the left-hand side of the S-plane. On the other hand, the fighter X-29 is unstable. It has at least one pole in the right-hand side of the S-plane. Have you ever tried to balance a stick just like this street performer? Actually, let's try it. That's not bad actually, that's quite nice. But you know, sometimes the street performer is tired and sometimes he does not balance the stick well enough and the stick can fall. Let's try to do what a street performer does when he's very, very tired. So how this performance is related to the S domain? Let's take a look at the two cases. At first, when the stick is being stabilized, we can see that everything is okay. Even though it goes back and forth, back and forth, back and forth, it's still stable. On the other hand, when it's unstable, it is the amplitude, as you can see, becomes larger and larger, and finally the stick falls. In the first case, where it's stable, the system, meaning the broom or the stick with the performer, are stable system. And all the poles are in the left-hand side, in the green part. In the second case, the performer and the stick are together unstable system, and there is a pole in the right-hand side of the system in this particular case, which is the red part of the S-plane. Now let's try to make an experiment. Find a stick and let's try to do the following. Hold the stick so your two fingers are just below it and start to move the fingers towards each other and watch what happens. What happened? Try to explain. Now you are at the center. Try to start to move the two fingers to the outside. Slowly but surely, one finger stays at the same location, the other one moves. Try to explain it in terms of feedback. I'll give you a hint. In the first case, this way, we had negative feedback. In the second case, we had positive feedback. Think about friction and what happens as a result. You will find the answer in no time. It also works with a broom. The stick does not have to be symmetric. Take a broom, do the same experiment back and forth, and you will see very similar results. Again, it's your call to try to explain what is really happening. It's about time that we talk not only about stability and instability, but we also talk about how close we are to instability. It's called margin, okay? How much margin we have until we get to instability. In the case of the airplane, we saw that the airplane's quote-unquote moves from the left-hand side to the right-hand side depends on the location of the paper clips. But we can do some more experiments with the stick, for example, as we're going to show next. Now we're ready to see degrees of stability using the sticks, or one stick actually. We're going to hold the stick at different locations. Where we hold it at the very top, it is quote-unquote very stable. As we move our finger lower and lower and lower, it becomes less and less stable until it goes to the borderline of instability, and then it becomes unstable. And we can see it with the behavior of the stick, or the dynamic behavior of the stick as a function of time. Look at the following graphs. It goes all the way from very stable, less stable, unstable, and even more unstable. Another example of borderline stability, stability, and instability, again, it's only for illustration purposes, is when you have two cars on the highway moving towards each other. When the lanes are very wide, the chance to have an accident is close to zero. When the lanes start to be very narrow, they are almost touching each other. But when the lanes cannot contain both cars, obviously they are going to collide. We showed it as green for stable, yellow for borderline, and red for unstable. Now, by the way, the borderline is considered also unstable under BIBO. One last example, which is slightly more quantitative. Think about jump rope. When the rope is far away from your legs, you are safe. You're not going to, trip. This is shown in green. Then, when the rope is very close to your feet, it's the borderline. It's almost tripping, almost there. But when the rope is touching your legs, obviously it's red and it's unstable, quote-unquote unstable. Again, only for illustration. Now, what's the point here? We can also measure, there is a way to measure how close we are to instability. It's called phase margin and gain margin. Phase margin tells you how far you are from the point of instability. In control systems, it's a negative 180 degrees. So the farther away you are from negative 180, the better. What does it mean farther away? If the system is negative 130 and instability borderline is negative 180, from negative 130 to negative 180, we call it phase margin of 50, which is good. So it's a positive phase margin. The phase is closer to zero than negative 180. On the other hand, if the phase is more negative than negative 180, it becomes unstable. We call it negative phase margin. Okay, quick summary. For a system to be BIBO stable, all poles, no exception, must be in the left-hand side of the S-plane. some systems, not all of them, some systems we can make them stable with the correct design. We can change the design of the system or add controllers actually to make them stable in closed loop. Not all of it, not all the time, by the way. Sometimes it's not possible. And we also have a way to measure instability or how close we are to make the system unstable. One measure is phase margin. Next, we are going to show you an experiment so you can do it at home and try to understand the meaning of stability. We are going to have two cases, very similar cases of motion of cones on a slope. One of them is a stable system, the other one is unstable system. Try to think about it and figure out why one is stable and the other one is unstable. On behalf of Jorge Jimenez and myself, we would like to thank you for watching, and we hope that you understand now stability slightly better. Thank you very much.